Welcome to lecture 52. This is week 11 and in this week we will be talking about applications of optimization. In our previous lecture we have talked about the use of fmin_con and fsolve, which are solvers available in MATLAB's optimization toolbox. So, we took an example of CSTRs in series and demonstrated the use of fmin_con and fsolve for solution of an optimization problem. Specifically, we had 3 CSTRs in series and a reaction of the type A2 products was taking place in each of these reactors. So, we want to find out the optimal values of the volumes of the CSTR, so that the concentration of the reactant A in the exit stream of CSTR3 is minimized. In other words, we wanted to convert the maximum amount of A to products. So, today also we will take similar examples and continue our discussion on applications of optimization. So, as first example, we are again taking the case of continuous star tank reactors in series, but this time we are thinking that there are n number of reactors in series. Each reactor has the same volume and we want to find out the optimum number of the reactors in this train, so that the total cost is minimized for a specific change in concentration of the inlet reactant stream. So, let us try to understand the problem first. So, we have n number of CSTRs in series. So, an inlet stream with concentration Ca1 in enters CSTR1. The first order reaction A2 products is taking place in each of these CSTRs. So, the outlet concentration of CSTR1 is the inlet concentration of CSTR2. The outlet concentration of CSTR2 is the inlet concentration to CSTR3 and so on and so forth. The design equation for the CSTR is given as CAI out equal to CAI in divided by 1 plus kV by Q for I equal to 1, 2, 3 up to n. So, if we want to write, let us say for the first reactor CSTR, we will write as CA1 out equal to CA1 in divided by 1 plus kV by Q. Similarly, you can write for CSTR2, 3, so on and so forth. Now, CA1 out is the outlet concentration of CSTR1, CA1 in is the inlet concentration to CSTR1, K is the first order rate constant, which is given as K equal to 12 hour inverse, V is the volume of each reactor, V meter cube, and Q is the volumetric flow rate of these streams, which is 0.9 meter cube per hour. So, the volumetric flow rate of the stream Q equal to 0.9 meter cube per hour is fixed for all the reactors. So, that we understand the design equation for the CSTR. The cost of a reactor depends on its volume and is expressed as cost equal to 137000 into V to the power 0.4. The desired concentration change is Ca1 in by Can out will be 10,000. So, this concentration divided by this concentration will be equal to 10,000. So, we want that if we have n number of CSTRs in series, the outlet concentration, the concentration of A in the outlet stream will be 1 by 10,000 of the inlet concentration of A into the CSTR 1. So, this is my desired concentration change. So, I have to find out the optimum number of reactors in the train so that the cost is minimum. So, find out the optimum number of CSTRs. So, this was the design equation. Ci out equal to Ci in divided by 1 plus Kv by Q. Now, you understand that the outlet concentration of a CSTR is the inlet concentration to the next CSTR. So, Ca1 out equal to Ca2 in, Ca2 out equal to Ca3 in up to Ca n minus 1 out equal to Cn in. So, now combining this and this, then we can write that Ci out equal to Ci in by 1 plus Kv by Q, and this Ci in is basically Cai minus 1 out. We know that the inlet concentration to a particular reactor number I is basically the outlet concentration of the reactor I minus 1. So, Cai in equal to Cai minus 1 out. Note that this is valid for I equal to 2, 3 up to n, starting for 2. So, now if we apply this recursively, we will be able to write Cn out equal to 1 plus Kv by Q to the power minus n Ca1 in. what will happen basically is, if you use these things recursively, you will be able to write CA 1 note this, how this CAN out and CA1 in are related. This equation needs to be applied recursively. If you do that, what we will get is CAN out 1 by 1 plus kV by Q 1 plus kV by Q in such term when you have here CAN 1 in. So, this leads to 1 plus kV by Q to the power minus n CA 1 in. So, that is what you get this expression. Now, what is the desired change? CA 1 in by CA 1 out equal to 10,000. So, from this 2 you get 1 plus kV by Q whole to the power n equal to 10,000. Note that n is the number of CSTR units in series. Q is given as 0.9 meter cube per hour, K is given as 12 hour inverse. So, from this we can get an expression of V. So, we get V equal to 40 by 3 square root n 10,000 minus 1. So, I have been able to express V as a function of n. Note that this V is the volume of each reactor. Now, the reactor cost is given as 137000 into V to the power 0.4. This is for each reactor. So, for n reactors you must multiply this by n. So, the cost expression is cost equal to n into 137000 V to the power 0.4. Now, we have been able to relate V with n here. So, let us substitute V So, that is what we are doing here. So, by substituting the relationship of V and n, we are able to express the cost expression as a function of n alone. So, to find the minimized cost, we now have to find the value of n that minimizes the cost as represented by this expression. So, note we have an unconstrained function of single variable. So, my objective function is minimize the cost function, find out n and minimize the cost function. So, we have this unconstrained minimization problem in single variable. We can use fmin search of MATLAB optimization toolbox to solve this problem. If you remember, fmin search uses simplex algorithm to solve the problem. So, first thing, you write the equation for the cost function in a function file as shown here. So, I define a function called cost, function c equal to cost of n, and there I am writing the expression for the cost, which is a function of n, and n is the decision variable, that means the number of CSTR units which are connected in series, optimum number of CSTRs. Now, you write these expressions on MATLAB command window or write a script and run the script. So, give the initial guess. Let us start with a guess that n equal to 2. So, n 0 equal to 2. You can give the options to display the results of each iterations and to define the tolerance, and then you call fmin search solver using fmin search at cost. So, name of the function where you are defining the cost, n 0 is the initial guess and options is instruction to the solver to display the results and to set the tolerance at 10 to the power minus 8. The output will be n, which is the optimal number of CSTR units, and f val is the function value at this optimal number of CSTR units. That means, the cost associated with the optimal number of CSTR units. So, if you run this program, you will get n equal to 4.12 as the minimum optimal value of n, and the optimal cost associated with n equal to 4.12 is 37 lakhs 17,000 something. So, although the value is slightly greater than 4.12, we can, let us say, consider the optimum number of reactors that are required is 4. So, if we consider that, the volume of each reactor can be computed now, because we know the relationship between the volume and the number of CSTRs n, and this gives me the volume of CSTR as, each CSTR as 120 meter cube. So, this is how we could solve the unconstrained minimization problem associated with the cost minimization of a CSTR train. So, this number of CSTRs connected in series are known as a reactor trains. So, we found out the optimum number of CSTRs required in the series, so that the total cost is minimized and we obtain the desired change in the inlet concentrations. As in second example, let us find out the optimal diameter of a pipe. In a chemical plant, the cost of pipes, their fittings and pumping are important investment. Consider the design of a pipeline L feet long that should carry fluid at the rate of Q gallon per minute. The selection of economic pipe diameter D in inches is based on minimizing the annual cost of pipe, pump and pumping. Suppose the annual cost of a pipeline with a standard carbon steel pipe and a motor driven centrifugal pump can be expressed as this expression. So, the annual cost is expressed as a function of the pipeline length L, the pipe diameter D and HP associated with the motor, where HP is given by another expression which is a function of L the pipeline length, D the pipe diameter and the flow rate of the liquid Q. So, basically the cost can becomes a function of L, D and Q, because HP is a function of L, D and Q. So, if this HP is substituted, the cost becomes a function of L, D and Q. So, let us formulate an appropriate single variable optimization problem for designing a pipe of length 1000 feet with a fluid rate of 20 gallon per minute, so that the cost is minimum. The diameter of the pipe should be between 0.25 to 6 inch. So, we found that the cost is basically a function of L, D and Q. Now, we are specifying the pipe length L at 1000 feet and the Q, the flow rate we are specifying at 20 gallon per minute. So, basically the cost becomes now function of pipe diameter alone. So, we want to formulate an appropriate single variable optimization problem for designing a pipe length of 1000 feet with a fluid rate of 20 gallon per minute, so that the cost is minimum. And we also have a lower bound and upper bound on the pipe diameter. So, the pipe diameter should be between 0.25 to 6 inch and the cost is given by this expression. So, it is now straightforward to identify the objective function. The objective function is nothing but the cost. So, after you have replaced the expression of HP into the expression of cost and you have substituted L equal to 1000 and Q equal to 20, you will obtain this expression as an expression for cost. and we have bounds on D because D has to lie between 2.5 and 6. So, to solve, let us first write the equation for the cost in a function file. So, let us write down the function file. So, I define a function called pipe dia. So, function f equal to pipe dia, argument is d. D is the pipe diameter. So, this is the expression for HP and this is the expression for the cost. So, this is equal to f. So, output of this function is the cost for given pipe diameter D. So, now you can use fmin_con to solve this optimization problem. Define the initial case, we do not have any linear inequality or linear equality constants. These are the bounds on the decision variable. D has to lie between 0.25 and 6 inch. So, this is 0.25 then. Idea is this, that there is an upper bound and lower bound on the decision variable. So, we do not have any linear inequality or linear equality constant. We have an upper bound and lower bound on the decision variable x. So, now you call the fmin_con solver following the appropriate syntax. So, first is the name of the function file which will return the objective function value. Next is the initial case for the solution. So, initial case for the pipe diameter. Next, A and B1 corresponds to Ax less or equal to B, which I do not have. Then next two are for A equality x equal to B equality, which again I do not have. And then we have lower bound and upper bound, and we have defined those as LB equal to 0.25 and UB equal to 6. I do not have nonlinear constants. So, supplied null and then options. We have supplied options to define maximum function evaluations 10,000 and to display the results at each iteration. So, the output it gives is the optimal pipe diameter and the function value at this optimal diameter, that means cost at this optimal diameter. So, the result is D equal to 0.825033 and the optimal cost is 796.64 in appropriate unit. So, the optimal diameter is obtained as 0.8250. So, this was an unconstrained single variable optimization problem. So, in this lecture we talked about two single variable unconstant optimization problem. The first one is solved using F-min search. That was a problem where we found out the optimal number of CSTers in the reactor train. And next, again we solved a single variable unconstant problem, but this time we solved using F-min con. So, you can also solve this problem using F-min search. And I will suggest that you solve this problem using F-min search as well and compare the results. So, this is if you draw the cost versus the pipe diameter. So, you basically have an expression for cost versus diameter. So, what you can do is between 0.25 to 6 inch you can generate the D values and can obtain the corresponding the cost values using this expression. And then if you plot, you will get this plot. So, this plot is nothing but the direct use of the cost function expression for various values of the pipe diameter D. So, this is since this is a single variable optimization problem, you can obtain the optimal value of D simply by plotting. So, you can see that here also the value is about 0.82. So, the minimum lies here. So, we will have confidence in our result and we conclude the optimal pipe diameter is 0.8250 inch. So, with this we will conclude our lecture 52 here.